All right, let's talk about stream processing. It's one of those terms you hear all the time, but what does it actually mean? Well, it's the engine that powers pretty much everything in real time today, from your social media feed updating instantly to your bank flagging a weird transaction. So, in this explainer, we're going to pull back the curtain and see exactly how it works. Let's dive in. I really wanted to start with this quote from John Gall. A complex system that works is invariably found to have evolved from a simple system that works. It's just perfect for this topic. See, stream processing feels super complicated, and it can be. But it's not some magic that just appeared overnight. It's actually a really clever evolution of simpler ideas that already worked pretty well. It's the next logical step for a world that, let's be honest, never, ever stops creating data. Okay, so here's what we've got on deck. First, we'll go from batches to streams. Then we'll look at the event stream highway, how this data actually moves around. After that, a really cool idea, how databases become streams. Then we'll see how to put it all to work. And we'll finish up with a little wrinkle in time. Let's get to it. All right, section 1, from batches to streams. The big question here is, why? Why did we need to move past the old way of doing things? Well, it boils down to one thing really, the need for speed. So let's break this down. The old way of doing things was batch processing. You can think of it like developing a roll of film back in the day. You'd go out, take 24 pictures, right? That's a bounded, finite set of data. Then you'd take the whole roll to get developed, and maybe a day later you'd get your photos back. The problem is, the moment is gone. That's high latency. Now, compare that to stream processing. This is like a live video feed on your phone. The data is unbounded. It just keeps coming. It's an infinite stream. And we process every single frame, every event, as it happens. That's how we get that low latency, real-time feel that we now expect from, well, pretty much everything. Okay, so if we're going to have this constant flow of data, we need some serious infrastructure to handle it. Think of it like a massive digital highway. Let's talk about how this data actually moves. The most basic thing driving on this highway is what we call an event. So what is an event? It's just a small, self-contained, and, this is key, immutable fact. Immutable means it can't be changed. It's a record that something happened at a specific point in time. It could be anything, really. You clicked a link, you bought a coffee, a sensor on a machine reported a temperature. It's a tiny little packet of truth that just says, hey, this happened. So it sounds simple, right? You've got producers, things that create events, and you've got consumers, things that need to do something with those events. A producer sends an event to a consumer. Easy. But what are the big challenges here? What keeps engineers up at night? Turns out there are some really tricky problems to solve. It really boils down to two huge questions. First, what if the producers are just way faster than the consumers? What if you're getting 1 million clicks a second, but your system can only process 100,000? That's a buffering problem. Do you just start dropping data? Do you tell the producer to slow down? Or do you find a way to queue it all up? And second, the big one, what happens if a machine just crashes? Poof, it's gone offline. How in the world do you make sure that the messages it was supposed to handle don't just disappear forever? That's durability, and it's absolutely critical. Okay, so this diagram shows two classic ways to deal with this. On the left, in part A, we have what's called load balancing. A producer sends a stream of messages, M1, M2, M3, M4. And you can see how the system splits the work between consumer 1 and consumer 2. M1 and M3 go to the first one, M2 and M4 go to the second. It's exactly like having two cashiers at a grocery store. They're sharing the load to get through the line faster. Now look at the right side, part B. This is called fan-out. It's totally different. Here, when the producer sends a message, like M1, it gets copied and broadcast to every single consumer. So both consumer 1 and consumer 2 get a copy of M1. This is for when different parts of your system all need to know about the same event. But here's where things can get really messy with some older messaging systems. Let's walk through this picture. We have two consumers again. Consumer 2 picks up message M3 to work on it. But then, disaster strikes. That little starburst shows it crashes. Now the message broker is smart. It knows M3 was never finished. So, trying to be helpful, it re-delivers that message. But it gives it to consumer 1. Here's the problem though. Look, consumer 1 has already moved on and processed message M4. So now it processes M3 after M4. The original order of events, M3, then M4, is completely scrambled. For a lot of systems, like financial transactions, this is a total disaster. You can't have this happen. So how do we solve that nightmare scenario? Well, we need a totally different way of thinking about this. What if messages weren't just temporary tasks that you process and then delete? What if instead we treated the stream of messages like a permanent, unchangeable record, an append-only log? And this is what that looks like. It's a really elegant solution. Producers don't send messages to consumers directly anymore. Instead, they just write their events to the end of a log, one after another. You can see the log is broken up into partitions to help it scale. Now, look at the consumers. They aren't pulling messages off and deleting them. No, they're just reading the logs sequentially. And see that little number, the offset? That's like their personal bookmark. They're just saying, okay, I've read up to position 4. And the next time they connect, they start at position 5. The beauty of this is that within a single partition, the order of messages is set in stone. It's guaranteed. So this table really sums up the huge difference in philosophy here. The old-style brokers, they see a message as a temporary job. Once it's acknowledged, it's gone, a destructive read. But log-based brokers are completely different. The messages are durable, they stick around, and consumers perform a non-destructive read. This is a game changer. It means the data is replayable. A consumer can crash, come back, and just start reading from where it left off. Or a whole new consumer can come online and read the entire history from the very beginning. That's a genuine superpower for building data systems. Okay, now we get to what is, for me, the most mind-blowing part of this whole story. This is where we take the idea of a log and apply it to our databases. This is truly the big aha moment in stream processing. So first, let's set up the problem. It's a super common one. You need to keep your main database and, say, a search index perfectly in sync. The obvious way to do it is what we call dual writes. Your application just writes the same data to both systems. But look what can happen. This diagram shows a nasty race condition. Client 1 updates a record to A. It writes to the database, then it tries to write to the search index. But right after, Client 2 updates the same record to B. It also writes to the database, then the search index. Because of random network delays, the write A command to the search index actually arrives after the write B command. The result, your database says the value is B, which is correct, but your search index says the value is A. They are now out of sync, maybe forever, and you have a silent ticking time bomb in your system. So how do we fix this? With a brilliant technique called change data capture, or CDC for short. The idea is simple. Stop writing to 2 places at once. Instead, your application does one thing and one thing only. It writes to the database. Then we use CDC to basically listen to the database's own private journal, its transaction log. Every single change that happens in that database gets captured and turned into an event stream. It's like putting a microphone on your database and broadcasting everything it does. And this is the result. It's so much cleaner. The database is now the leader, the single source of truth, period. It produces this ordered stream of changes. And everything else, the search index, a cache, an analytics system, they all become passive followers. Their only job is to listen to that change stream and apply the updates in the exact same order they happened in the database. The race condition we saw before, it's literally impossible now. We've designed it out of the system. This all leads to this really profound idea, which you can think of using a calculus analogy. The current state of your database, what's in it right now, is really just the sum of every change that has ever happened to it. That's kind of like an integral. And the stream of changes itself, that's the derivative. They're just 2 different ways of looking at the exact same information. And this is the deep insight. The log, the stream of changes, is the real source of truth. The database itself is just a cache, a snapshot in time of that truth. Okay, so we've gone deep into the theory, the how of it all. Now let's get practical. What kind of cool stuff can we actually build with stream processing? Well, there are a few big categories. There's complex event processing, or CEP. This is all about finding the needle in the haystack, looking for specific patterns in a massive flow of events. The classic example is fraud detection. See a credit card used in Boston and then 1 minute later in Singapore? That's a pattern you want to flag fast. Then you've got stream analytics. This is your real-time dashboard. How many people are on the site right now? What's the average order value over the last 10 minutes? Stuff like that. Materialized views is what we just talked about, keeping things like caches and search indexes perfectly up to date. And finally, there's search on streams, which kind of flips the whole idea of search on its head. Instead of having a bunch of documents and running a query against them, you have a stored query, like tell me whenever someone mentions my product, and you stream the entire internet's fire hose of data past your query. All right, last section. And we've saved the trickiest, most mind-bending problem for last. We need to talk about time. This is so important. In any stream processing system, there are actually two different clocks running. First, there's events time. That's the timestamp that's actually in the data. It's when the user actually clicked the button, when the sensor actually took its reading. It's the real-world truth. But then there's processing time. That's just the time on the server's clock when it finally gets around to looking at that event. And because of network delays, queues, all sorts of things, these two times can be seconds, minutes, or even hours apart. And if you mix them up, you're going to get some very wrong answers. Let me give you a perfect example. Let's say your processing system goes down for just 1 minute for a restart. When it comes back up, it has a minute's worth of data to catch up on, right? So it chews through that backlog as fast as it can. Now, if you're plotting a graph based on processing time when the server saw the data, it's going to look like you had this insane, massive spike in user activity. But it's an illusion. If you plotted the exact same data using event time when the users actually did those things, you'd see the activity was just nice and steady the whole time. Using the wrong clock created a completely false picture of reality. So that's the big takeaway, and the question I want to leave you with. The next time you look at any real-time chart or dashboard, ask yourself this one simple question. Am I looking at a picture of when things actually happened? Or am I just looking at a picture of when my computer noticed they happened? Because as we've just seen, those can be two very different things. Thanks so much for watching.